If your model happily outputs 0.9 confidence and is wrong half the time, you cannot safely use those scores in the real world. We will check calibration in Python and apply simple fixes so predicted probabilities match observed frequencies. You might already trust a model because its accuracy looks fine, but decisions depend on probability, not accuracy. I will show you how to measure that trust and how to nudge probabilities so they reflect reality. By the end, you will see common failure modes and a simple temperature trick that often fixes them. I'm Professor Pi, teaching AI foundations from basics to advanced with simple concepts-first Python that helps you solve bigger real-world problems. Calibration matters when probabilities drive choices. Imagine a classifier that flags fraud and reports its confidence. If confidence is wrong, you either ignore useful alerts or chase false leads. Calibration sits between model training and decision-making. It is a lightweight step that keeps probabilities honest. Success is when predicted probabilities line up with observed frequencies. On small toy data, you can visualize this. In production, you use the same checks on held-out validation data. At its core, calibration asks one question. When the model says 60%, do those cases happen about 60% of the time? If yes, trust the score. If not, fix the mapping from scores to true probabilities. Strengths include simplicity and interpretability. Weaknesses show up with tiny data or extreme class imbalance. We will build a tiny one-dimensional example where labels flip at 0. That makes it easy to see overconfidence, to measure Brier score and expected calibration error, and to apply temperature scaling. Think of logits as raw confidence before the sigmoid. Now we jump into a first diagnostic. This snippet builds a tiny classifier and reports its Brier score. We create a simple one-dimensional dataset X with binary labels Y that flip at 0. The list P holds uncalibrated probabilities from a steep sigmoid, which tends to be overconfident on this toy. The variable num accumulates squared probability errors, and B divides by the number of examples to get the Brier score. A lower Brier means probabilities better match outcomes. Higher suggests miscalibration or inaccuracy. The printed Brier summarizes baseline probability quality before any calibration. Now we slice data into reliability groups to quantify average gaps. This snippet estimates calibration error using equal frequency bins. We sort the pairs of probabilities and labels so nearby confidence values sit together. The list GS slices the sorted data into M groups of similar size, which act like reliability bins. For each group, we compare average confidence to average observed frequency and weight by the bin share, summing to an expected calibration error. Increasing M gives a finer view but makes each bin noisier with small data. The printed ECE shows how far confidences deviate from actual outcomes on average. Next, we focus on the highest confidence predictions. This snippet checks overconfidence among the most confident predictions. We sort the probability label pairs by confidence descending and keep the top K entries. The variable conf is the average predicted probability for these top items, while AC is their empirical accuracy. The gap shows how much the model's confidence overshoots or undershoots reality. In the high confidence regime, increasing K smooths the estimate, but mixes in less confident points. The printed top gap quantifies whether strong claims match observed correctness. Now we search for a simple global fix that rescales confidence. This snippet fits a temperature to calibrate probabilities by minimizing NLL. The function loss computes negative log loss after dividing logits by a temperature T, which softens or sharpens confidence. We search a small grid from 0.5 to 3.0 and pick the T with the lowest loss. Smaller T makes the sigmoid steeper and pushes probabilities towards 0 or 1. Larger t pulls them towards 0.5. On noiseless labels, a smaller t often improves NLL. With noise, too small t can overfit. The printed NLL confirms how well the chosen temperature matches outcomes. Next, we measure calibration after applying that temperature. This snippet evaluates calibration after applying the learned temperature. The list Q holds recalibrated probabilities produced by dividing logits by t and passing through the sigmoid. We sort the calibrated probabilities with labels, partition into equal frequency bins, and compute the weighted gap between average confidence and observed frequency in each bin. This mirrors the earlier ECE, but now measures the effect of temperature scaling on reliability. If you increase M, you get a finer diagnostic but need more data to keep bins stable. The printed calice shows how much calibration aligned. Bringing this toy example to a real system is straightforward. Replace the one-dimensional inputs with your model logits on validation data. Compute the same Brier score and ECE. Fit the temperature on a held-out fold. Then apply it at inference time to convert logits into better calibrated probabilities. This keeps the model unchanged and preserves ranking while improving trust in scores. Recap in 3 points. What it is: calibration makes predicted probability match observed frequency. When to use it: anytime probabilities drive decisions or risk thresholds. One caveat: global temperature scaling fixes overall sharpness, but cannot fix class-dependent errors or features the model never saw. For a next step, tune the calibration procedure on a larger validation split and compare equal frequency bins to equal width bins. Or swap temperature scaling for isotonic regression to see which matches your domain better. If AI Foundations in Python help, subscribe and watch the AI Foundations videos.